into some big trouble when they are deployed in the real world. So, for example, you can imagine this self-driving car, and you put on the self-driving car your latest and greatest fancy machine learning techniques, and you're ready to deploy. But of course, you also want the car to be safe. The problem is that you have a limited budget for testing. So the question is, how do you spend this budget? And so what we are trying to do in this work is that we are trying to come up with clever ways of estimating the failure probabilities. Okay. So the problem setting is this. So as I said, we assume that an agent is being trained, maybe with RL, some other techniques, it doesn't really matter. But at the end of the day, you have this agent that you trained during many, many hours. And at the end, you want to find out whether this agent is going to fail in a catastrophic way in some settings. And there are two different settings, or two different questions that we'd like to answer. So one is more like a debugging approach. So people are often interested in creating situations where their agents do fail. So that's one of the settings. The other setting is more classic. That's related to the Rayleigh simulation literature. There you want to estimate the probability of a failure. And since you did a good job at training your agent, this probability is going to be very small, hence the name Rayleigh simulation or Rayleigh probability estimation. So the success criteria for methods that attempt to do this are basically how much time or how much resources do you use for the testing, right? So you don't want to run the car for lots of time. Finally, so why do we care about failure probability? So why you may train your agent and you might believe that it is robust, and it is maybe mostly robust, but even the best trained agent might have some failure cases, right? So there could be some boundary cases where anything breaks. Maybe some failures are even inevitable. So one way to then address this question of then what can you do if failures are inevitable is to assume that there is some natural probability distribution over the situations that you're interested in, and then you want to estimate the failures under that distribution. So it's not just like, find me a failure. Yes, failures will exist, but under the natural occurring distribution, what is a failure probability? So as I already mentioned, there is big literature on rare event estimation. In this work, we are claiming that none of those methods are particularly very easily adaptable to this setting. And if you want to know more why, then my colleagues are going to gather a poster and you can ask them. Okay, so what is the main idea of the work? So the main idea is very simple. It's kind of like copying what people would already do. So when you're training your agent, maybe during training you observe that the agent has failed, and you save those failures, and then once you have your final agent that you produce, maybe you want to test that agent at least on those failure cases, kind of like regression testing. But of course, this may not work because, well, if those cases were, let's say, included in training, then the new agent may never fail on those cases. So we have to refine this technique a little bit, and that's exactly what we do in this work. Yes.
One question is, when you say chance of failure, so are you integrating over the chance that the difficult situations may arise, or
right? So there is a naturally occurring distribution of the initial conditions or settings or problems, and I'm integrating over that distribution. Okay. So, all right. So the method, as I kind of hinted on it, is a simple approach. So we want to learn to identify these difficult situations. And the way we do this is that we are building a predictor that given a situation predicts the probability of failure given for that situation, right? So many of these environments are random, so the agents may or may not fail. We are going to use the data that is generated during training to train a probability predictor that tries to predict the probability of failure. Okay, and then once you have done this, the rest is kind of easy. You're going to use inference weighting. It's kind of like a I don't know, like it's an embarrassingly simple idea. So you're going to use inference weighting to correct for the bias that would come from using somehow this probability of failure. You want to bias your samples towards this, so you're going to do that. And you're going to use inference weighting corrections to correct for this or some other methods. In this case, at the end, we decided to use rejection sampling. So very simple. Okay, so that's the idea. And to get some formalism, so let's say you have this trained agent A, and you're running episodes from some initial state or initial configuration or situation distributed according to this distribution. You assume that you can sample from this. So for example, this could be the initial position of the car, or it could be the shape of a track that the car has to drive on, or both. And then you're going to have a failure indicator that you can observe, and there is some additional source of randomness there, which may come from your agent, or it may come from the environment as well. At the end of the day, nevertheless, for any initial position and any such unobserved random input, you're going to observe either a failure or no failure. So it's a binary indicator variable. And your goal is just to estimate. So you're integrating over both the initial configuration and this unknown source of randomness. Your goal is to estimate the failure probability. And your goal is to minimize the number of variations that you need to estimate this well. So there is the ideal failure probability predictor, which is just the probability that given, sorry, conditioning is missing here, sorry about that. So given X, the probability that failure happens under Z, it gives you the probability of failure. And so as I said, we're going to just learn an approximation to this using some kind of technique. Very often you end up using neural networks with cross-entropy loss, for example. That's one of the choices, but you could use any other techniques to do this. And then to address the two problems, in the first problem, you wanted to search for some failure. And for that, you're just going to use some global optimization method in a way. And one way of doing this, which seems to work well, is to sample. It's a very simple, again, embarrassingly simple method. Sample a bunch of initial conditions, evaluate your predictor of failure at these initial conditions, and just choose the initial condition for which this predicted probability is the highest, and then test on that. And then you can repeat. For risk estimation, you can use importance and rejection sampling. So interestingly, since there's these two sources of randomness, one is the initial condition, and the other is this environment stochasticity or agent stochasticity, the Z variable. The optimal proposal distribution is not the usual one, but it's a variation of that. You can easily get that. And this is the distribution that you want to sample from to minimize the variance of your estimates. So how do you do that? The way you can do it is that you just sample from the underlying initial condition distribution, so this P of X distribution, and you're going to use rejection sampling to reject this probability that is this probability to get a sample. And if you do this, then you can prove that this is a non-biased estimator. So finally, how do we learn this failure probability predictor? you can use these previous agents and learn from this previous agents' failures. So the good thing about this is that this data has already been generated. Generating data in these simulations is usually what is extremely expensive, so you don't want to, so if you can, you want to reuse data. You don't want to generate new data. Simulations are extremely expensive. Okay, so use this data and then you hope that this is going to work. So what's the intuition? Why would this work? So this figure is kind of like a toy explanation. So imagine that the setup for failures is this big box. And then somehow the assumption underlying this work is that the weak agents are gonna fail in this white box, and the strong agent is going to fail in a subset. That's the black box. And what the method essentially does is that rather than sampling from the huge box, the outside box, it is basically focusing sampling on the medium box. And since sampling initial conditions is cheap, this rejection sampling is pretty efficient. The simulation is expensive. You end up with an efficient method. And the boost compared to baseline methods can be really great, as we will see. So right, I'm going to skip that slide. Okay, so what if your failure probability estimator is a little bit off? Well, you might think about that you're going to sample from the part of the initial conditions that the agent doesn't fail. Then maybe your method is going to be worse than the crude Monte Carlo estimator. You can correct for that by mixing in the crude Monte Carlo estimator. With this, you can guarantee that you never use, let's say, more than twice the number of samples than the crude Monte Carlo estimator, but you have a huge potential upshot of improving upon the baseline. So that's one simple way of robustifying it, and there are many other ways as well. So finally, so we tested this in two domains, in Torch and the modular simulator, humanoid, and in Torch. The problem was to predict the probability of crash over random tracks. And in Mujiko, the problem was to predict the probability of fall over random initial standing conditions. And so we're going to have three sets of results. So for the failure search, so here you're trying to find a single failure of the agent. So it's like for debugging. You can see that, so what these graphs show is that you have the two evaluation strategies. Blue is the standard, or like when you're not biasing the search towards any initial conditions. You can see that this is highly inefficient, so the y-axis is the number of episodes until you observe a single failure. So you can also say that this was a great agent, but notice that if you use the method that we developed, then you don't need much time to detect failures. So there are actually a lot of failures. And the results are kind of similar on both domains. The speed up is like 50 times on Torch and over 500 times on the humanoid domain, and these results tend to be pretty robust. So that kind of shows that there is a huge room for improvement, and it also shows that this sparse sense of security or safety can truly be a bottleneck if you're not using any clever method to detect these failures. So the next experiment was failure rate estimation. So here we are running many experiments, and we are trying to we are estimating the probability of or estimate a confidence interval around or estimate not containing the true failure probability, which was estimated in a very long simulation. And you can see that the blue curve shows our method, and the green curve is just a baseline, the crude Monte Carlo method. You can see that there is a huge advantage to the more clever method. It's roughly 11 times better on Torch and 17 times better on. Finally, you can also use this work for things like finding the agent that's the most reliable amongst a set of agents. And again, the story kind of repeats. I won't spend more time on this. You can imagine that you can apply this method in this situation and beyond. So what are the takeaways? So one of the big first takeaways is that we have this single reward hypothesis in reinforcement learning, that the reward function is going to contain all the information that is needed to optimize your agents. But in the case of when you worry about these catastrophic failures, this may become extremely challenging. In this work, we have seen that even just evaluating the agents, if you're not doing something clever, becomes basically impossible. So it is, I think, a very important research direction to maybe tweak our algorithms to take into account that the agents that you are trying to train should fail very, very rarely. And for this, there are lots of exciting research directions and more research to be done. All right, so with that, I'd like to conclude that this is just a fun problem to work with, even though we are talking about catastrophes, events. It's been really a great pleasure to work on this problem because it's there is so much room for improvement and more work needs to be done. Thank you.